From the dawn of time, we have continuously worked on ways to improve our creations. Artisans, manufacturers, scientists, and engineers have for centuries manipulated the materials they work with to produce better products. Experimentation has included changing or controlling such elements as temperature, pressure, and composition to achieve steps forward for innovation. However, for all the manipulation and control these inventors exerted over their productions, the constant pull of gravity was one element they were unable to subjugate. Gravity is a constant force and an invisible element that controls the way many of the things we use in life and work. But where scientific research is concerned, gravity can impose many restrictions. Scientific experiments involving fluids whereby components such as sedimentation, fluid density, buoyancy, and temperature differences are examined are severely limited on Earth. This is why experiments in microgravity are ideal for fluid experimentations, as the low gravity effectively eliminates sedimentation and buoyancy issues. The Space Shuttle contains a space-based laboratory and presents scientists with a new environment in which to conduct experiments. Because the environment is in a situation of microgravity, gravity is no longer a constant force for experiments. This results in a whole new range of research opportunities available to scientists in many fields of study. Astronauts are often described to be experiencing zero gravity in space. The term, however, is technically incorrect, as even at 300 kilometers into space, gravity still exercises 90% of the attractive force it has at the Earth's surface. The concept of microgravity is a simple one. Once the shuttle reaches its orbit above Earth, it is traveling at a fast enough speed to maintain a continuous free-fall effect. This free-fall environment in turn creates the microgravity conditions that make things appear as they were floating, when in actual fact, they are falling. We experience microgravity when bouncing on trampolines, riding roller coasters, or diving off a diving board. Over 200 years ago, inventor William Watts discovered that he could produce superior musket balls by dropping molten lead from a tall tower. Since then, scientists have carried on this concept with experiments conducted in taller, more sophisticated drop towers, or in research aircraft such as NASA's KC-135 or suborbital rockets. But even with such advances in technology, periods of free fall are still limited to less than 10 minutes. On the Space Shuttle, however, scientists can experience more than 2 weeks of microgravity. The International Space Station is a more permanent microgravity research facility which can host experiments for long periods of time and can facilitate experiments into areas such as fluid physics. On Earth, liquid is considered as drops, streams, puddles, or even just the shape of the container it is occupying. In microgravity, however, liquid has completely different physical characteristics. No longer bound by the abundant gravity of Earth, surface tension reigns, allowing the liquid to form into a near-perfect sphere. It becomes a self-contained vial of liquid, free-falling with the rest of the shuttle's cargo. This fluid physics experiment on the sphere of liquid uses the drop physics model. The drop itself is suspended due to the free-falling effect. The movement is caused by sound waves, which are being used to maneuver the drop. One-of-a-kind experiments such as these give fluid physicists an opportunity to test hypotheses that were formulated on Earth. What do you get when you cross a satellite with a blimp? A stratolite, a robotic broadband airship hovering in Earth's upper atmosphere. Its US developers are hoping to go where no communications platform has ever gone before, delivering line-of-sight wireless broadband and mobile phone signals to an area the size of Texas from a single transmission point. This is the star of the show, the 188-foot-long Stratolite prototype. The unmanned airship is designed to function as a relay platform while floating in the stratosphere 65,000 feet above the Earth. At $20 to $30 million each, they're a bargain compared to your average $250 million satellite. The first supernova to be seen in recent times was discovered in 1987 by accident. Astronomer Ian Shelton had photographed the large Magellanic Cloud from the Los Compaños Observatory in Chile. On checking the developed plates, a bright object was there that he did not recognize. Thinking it a flaw in the print, he walked outside to check, and in the night sky, saw a new star. Because it appeared so suddenly, he knew it had to be a supernova, one of the biggest cataclysms imaginable in the universe. Using the Global Computer Network, his discovery was told to the world by the International Astrophysical Union. The supernova is located in the Tarantula Nebula in the galaxy nearest to ours. It is still 170,000 light-years away though. It is a rare experience for a supernova to be visible to the naked eye, although in 1054, the Crab supernova was visible even in daylight. The new supernova was once a faint star, a blue supergiant about 15 times the mass of our Sun. The supernova occurs at the end of a massive star's lifetime, when its fuel is exhausted and it is no longer supported by the release of nuclear energy. If the star's iron core is massive enough, then it will collapse. In this collapsed core, the protons and electrons are forced so close together that they combine to form neutrons. In effect, it becomes a neutron star. If the collapsing star is big enough, its gravitational force would overcome even the forces that hold atomic nuclei together, and the core would then become a black hole. However, if the star is not big enough to form a black hole, the core collapses, but then explodes. This single explosion could release as much energy as 10 of our sized suns give out over their entire life. This is the explosion called a supernova. The energy emitted by a supernova is primarily composed of neutrinos particles that very rarely interact with matter. They are detected using huge tanks of purified water buried underground in mines. The neutrinos interact with the purified water and cause flashes of light. After the supernova was observed, experiments were set up to measure unusual radiation reaching Earth. The data was gathered from satellite systems as well as some instrument-laden balloons. They found extensive gamma-ray radiation. NASA also launched several rocket experiments which detected some of the scattered X-rays. Following the discovery of the supernova, several experiments measured extensive gamma-ray radiation. The data was gathered by NASA's Solar Maximum mission already in orbit around the Earth, and instrument-laden balloons which were launched in Australia. There were other rocket-borne missions, one being the International Ultraviolet Explorer, which observed the ultraviolet spectrum. Japan launched the Genga satellite, which detected some of the scattered X-rays. NASA's rocket experiments launched from Australia also experienced radiation over several wavelengths. Other rocket-borne missions and the International Ultraviolet Explorer observed the ultraviolet spectrum. These measurements revealed information about the density and temperature of the supernova and the formation of molecules surrounding the supernova and in nearby space. The Kuiper Airborne Observatory also flew several experiments over New Zealand to observe the infrared part of the spectrum. Since infrared wavelengths are absorbed by the air, the experiments were conducted high in the atmosphere. Scientists used the results to form better theories on the formation of planets and the history of the universe. Scientists were able to gain valuable insight into natural lithiosynthesis, the formation of heavy elements. This will allow scientists to gain a better understanding of the history of our Earth and the rest of the universe. Gold blocks like this, 3 of them, will finally put Einstein's theories about gravity to the test. The gold blocks are the heart of this experiment. Researchers will use them to detect gravity waves from distant cosmic masses such as black holes or supernovas. Each cube, floating free inside its own satellite, will form part of the largest scientific instrument ever built. A triangular detector 5 million kilometers on each side, sensitive to movements smaller than the width of an atom. But the predicted gravity waves are incredibly weak, too weak to be detected on Earth. At the Max Planck Institute for Gravity Physics in Hanover, researchers are tuning the lasers that will detect the slightest movement in the gold blocks. The technology will be tested first in a miniature version of one of the satellites named the LISA Pathfinder. If this mission goes to plan, 3 full-size LISA satellites will be launched. They'll be deployed around the Sun, following the Earth in its orbit, but beyond the influence of the Earth's gravity. Once in place, the 3 LISA satellites will switch on their infrared lasers and fix their position. The lasers will register minute movements in the floating gold blocks for analysis by researchers back on Earth. Albert Einstein noted that the detection of gravity waves would prove his general theory of relativity. But he also recognized that an experiment to detect them could not be built with the equipment available at the time. Einstein's general theory of relativity, published in 1915, paved the way for the discoveries of everything from black holes in space to lasers and semiconductors here on Earth. He predicted that movements in massive objects in space would create faint gravitational waves, like ripples on the surface of a pond. But he said that the waves would be so faint that they would be nearly impossible to detect. Now that's about to change. Since the beginning of mankind, he has looked at the stars and pondered their mysteries. These fascinating objects are so far away that we, or even robot spacecraft, can't go and study them directly. The only way we can learn about them is by studying the radiation they emit and send us at the speed of light across huge distances. That radiation consists of visible light that we can see through telescopes, but also invisible radiation, most of which doesn't even penetrate the Earth's atmosphere. The more successful we are at decoding the radiation messages, the more we can expand our knowledge of the universe. As light is made up of different colors, a telescope with a spectrometer can do the same thing with starlight that a prism does with sunlight. Each star has a unique color pattern. These color patterns are chemical signatures, and like fingerprints, they help identify the star. By looking at the detail of the color patterns or spectra, you can determine the temperature, pressure, and chemical elements in the star. Every element has its own distinctive color. As an example, neon gives off its very characteristic red color. In this tube is hydrogen, and it gives off its purple or violet light. These colors are at the opposite ends of the visible spectrum. For centuries, our only source of information of the universe was by observing visible light using bigger and more powerful optical telescopes. However, the information gathered was still limited. Then in the 20th century, it was discovered that radio waves were coming from space, and this changed our knowledge of the universe. The shuttle was used on one of its voyages to operate the Astro 1 observatory. This was one of NASA's first missions to study astrophysics, the science that investigates the size, mass, temperature, and chemistry of celestial objects like stars and galaxies. Studying celestial objects from observatories on the ground is like listening to music with the high and low notes filtered out. This is why it was important to observe from above the atmosphere. Just like ocean waves, light waves have high points or crests and low points or troughs. The distance from crest to crest is the wavelength, and different frequencies result in different wavelengths. Traveling at the speed of light, radiation vibrates in electromagnetic waves. The electromagnetic spectrum classifies these waves by using their wavelengths and frequencies. Although the spectrum is continuous, it has been divided into 7 categories for easier identification. On one end of the electromagnetic spectrum, radio and microwaves are used for cooking, communication links, and for radar. Radio waves are used for communication, usually in the form of radio and television broadcasts. Although infrared rays can't be seen, you can feel them as heat from the sun or a heat lamp. On the higher energy side of the visible spectrum are ultraviolet rays. To most people, ultraviolet rays are the ones that tan or burn their skin. This happens because although most of the sun's energy is invisible light, our sun is hot enough to emit some ultraviolet light. A small fraction of this reaches us on the ground. To astronomers, ultraradiation tells about hot young stars that have just been born, or hot old stars near their deaths. X-ray photons are even more energetic. When an X-ray picture is taken of your body, the bones absorb the rays while the soft tissue like your skin does not. This kind of picture provides your doctor with important information. Gamma rays have the highest energy and the shortest wavelengths of all. Certain radioactive material emits gamma rays. These rays are used in some forms of medical treatments. However, too much exposure will cause severe illness. The Astro 1 observatory was the first observatory that could simultaneously take ultraviolet pictures of objects, study their ultraviolet and X-ray spectra, and determine their brightness and structure. It has allowed scientists to view the universe in its entire energy range and thus opened a great window to the universe. But this is only a beginning to understanding the universe and its symphony of light. A new super telescope is training its eye on the night skies. The Southern African Large Telescope, or SALT, is the largest optical telescope in the Southern Hemisphere. Analyzing what it sees in space will be a prime focus imaging spectrograph. Spectrometers are designed to break light down into different wavelengths. The results provide astronomers with far more information than simple pictures. By studying the spectra, they can determine the makeup of distant objects like stars and black holes. The instrument uses sets of precise lenses. Fittingly for a telescope named SALT, one set of lenses is made of pure sodium chloride. Scientists say the telescope and its spectrometer promise a unique window to the southern skies, allowing them to probe the center of the Milky Way. Kiruna in the far north of Sweden is home to a unique science program. The remote and usually snowy hills of Swedish Lapland provide a safe place for launching and falling rockets. Unlike larger rockets that launch spacecraft into orbit, sounding rockets like this go up and then fall back down to Earth. They often carry experimental equipment that can be recovered and analysed. Esrange specialises in experiments during the brief period of very low gravity at the top of the rocket's trajectory. Among the tasks on board the European Space Agency's Maxis 6 mission is an experiment to study the physics of foam. A team from Paris Sud University in France, led by scientist Dominique Langevin, are at Esrange to witness this launch. The team uses microgravity to extend the lifetime of the foams they are studying. The November nights in Lapland are long, with temperatures plummeting down to minus 30 degrees Celsius. The night before the launch, the Aurora Borealis is visible in the sky. As dawn nears and the countdown approaches, the tension in the control room is evident. Years of work may depend on the success of Maxis 6. The moment of truth is at hand. After just a few minutes, experiment housing has split from the rest of the rocket and reached its correct trajectory. For the next 12 minutes and 40 seconds, the experiments are carried out in near weightlessness, the condition known as microgravity. When the time is up, the experiment housing begins the fall back to Earth. Later, the recovery teams locate the experiment housing about 90 kilometers downrange at the launch site. Because the freezing conditions here might affect the experiments inside, speed is important now. After using pure manpower to dislodge it from the snow, the housing is carried by helicopter and tractor back. At the base, the scientists are keen to get to the results of their work. The housing is taken apart and the first results are analysed. The experiments on board this launch have been a great success.